of the directors of the Concrete Society. We've got a very interesting presentation today, and I'm looking forward to it myself, of Prof. Mark Alexander. But before we start, just a few things from my side about the Concrete Society. So I'm just going to start going through my slides. We at the Concrete Society of Southern Africa, we work on a number of core values. They are modern and advanced, relevant, streamlined and efficient, objective, inclusive and loyal. And we try to adhere to these principles as we give the service to our members. We've got a number of committees going and quite a number of committees on the way to start. We've got, for example, the Inland Branch Committee, which Michelle Fick was just elected as chairperson. We've got the KwaZulu-Natal Branch Committee with Donovan Leach, Western Cape Branch Committee with Nicholas Jarrett. We've got a Ready Mix Concrete Committee, which I am chairing. We've got a FIB committee. Head of delegation there is Dr. Sarah Scorpin and Vice Kim Tim. And the Cement Branch Committee is currently chaired by Mark Hovey. We've got a few other committees coming soon, and you could maybe join them if you will see them in the next presentation. So we rely on members to be able to give a service like this presentation we do today. We rely on members to fund us, to fund our working, to fund what we do. Therefore, it's important that everybody becomes members that share in the advantages of the Concrete Society. Now, we are having these presentations open to the public over the whole world. If you want to get up in the middle of the night in America, you're welcome. Oh, it's actually not, it's morning there. But we would ask you to consider to become members, to support us financially and support us with your time so that we can really make this Concrete Society something worthwhile for everybody and something here to stay. There's different levels of memberships, individual memberships. It's only 1,500 Rand. And just to put it in perspective, you can get 2 CPD points a year by attending the concrete class and the concrete fix every year. That gives you 2 CPD points. And if you're just an individual member, that costs you 1,500 Rand. So just for 1,500 Rand, you can get 2 CPD points a year if you attend all these events. CPD points are unfortunately only for members. Everybody is welcome to attend, but CPD points goes to members. We've got company membership, we've got academic membership and associate memberships. And just to say a bit who are our members at the moment, we've got diamond members. It's the highest class of member or tier of membership, CRISO and Quick Group. We've got emerald members. We've got 5 at the moment, some new entries to this list. We've got Tanzanite members and another list of Tanzanite members. We've got the emerging enterprise member. We've got associate members. We've got academic members. And then just some upcoming events, some adverts. We've got the gala event of the Fulton Awards. It's going to be good. It's going to be great. It's on the 7th of June, 2025, this year, of course. So there's still some tables available. There's some seats available. There's some sponsorships available, or I think the sponsorships could be sold out by now. But inquire if you're interested. Maybe we can make a plan for you. The sponsors we've got so far is we've got an anchor sponsor, PTSS. We've got AfriSam, we've got Contest, we've got World of Decorative Concrete, and CRISO. We've got as our sponsors so far. Then we've got some more interesting concrete fixes. As you would have noticed, there's a concrete class and a concrete fix. There's a distinct difference between the two. A concrete class is what we've got today, is where we go back to basics, almost back to university or college or institute, wherever you studied, and we learn the basics all over again, and we sharpen our pencils in that way. that's a concrete class. The concrete fix is something very modern, very advanced technology, changing the industry, changing the way we're designing structures, changing, for example, durability repair. For example, this ultra durability repair and rehabilitation using crystalline technology will be the next on the 23rd of April. And then we've got one on the 21st of May. We've got Dr. Rod Rankin, extrinsic factors that alter true measured concrete strength. That can be very interesting, especially next time you fight about what is good enough, what's not good enough. And there's some other events as well. There's just for the Fulton Awards, we've got a presentation by Brian Perry and Stephen Humphreys and Daniel van der Merwe, the judges. They're going to speak about the Fulton Awards contestants, all the projects. Then there's another presentation by Mark Alexander, Prof. Mark Alexander in July. In August, we've got Kim Tim from Stellenbosch University on 3D concrete printing, which will also be very interesting to listen to. CONCRETEClass, the next one is alkali silica reaction, and that will be Dr. Janina Kanji from the University of Witwatersrand. Will be presenting that on the 8th of May. And then future concrete classes still be presented. I'm working on including some structural aspects as well. Up to now, we've had concrete mix design, durability, and aggregates, which is all concrete technology. We want to work towards structural design as well, structural design topics, layouts, whatever we want to talk about. So if you've got any ideas of what you would like to listen in the structural realm of things, structural concrete, you're welcome to contact me or Natasha at the Concrete Society. But then we've got in August, we've got Prof. Rian Kombrink going to speak about supplementary cementitious materials. Then the Western Cape branch has got a Careers in Concrete event coming up. If you're in the Western Cape, you can look out for that. CPD points, we give CPD points. It comes, I think, about 2-3 weeks after the event, and you'll get an email from Natasha when you receive them. And if you want to know anything more about the Concrete Society, contact us on the website or on the LinkedIn page, which is quite active, or contact me or Natasha directly. You're more than welcome to see how you can be involved and help make a difference. So thank you for your ongoing support and contribution. It's much appreciated. But now enough about me. You didn't come to listen to me speak. Our presenter today is Professor Mark Alexander, which is very well known in South Africa. And I want to firstly thank him for taking the time and the effort putting a presentation together for us. But just some background of him. He's an emeritus professor in civil engineering and a senior research scholar at the University of Cape Town. He has a PhD from the University of Witwatersrand and is a fellow of the University of Cape Town, of Rylam, of the South African Institute of Civil Engineers, South African Academy of Engineering, and the Indian Concrete Institutes. He's a jolly good fellow, I should add. He's a registered professional engineer in South Africa, and his research interests on the concrete durability, service life prediction, concrete sustainability, and repair and rehabilitation of deteriorated concrete structures. Mark, we look forward to your presentation. I'm going to remove this now from the screen. If I can just, while he's uploading his presentation, if I can just ask you if you could switch off your videos, it saves a bit of a bandwidth, makes it easier, and also keep your microphones muted. And at the end, we will have time for questions. So thank you very much, and we look forward to your presentation, Prof. Mark Alexander.
Thank you very much, Billy. All right, so what can you see on your screen at the moment?
I can see aggregates and concrete and appreciation of their role.
Is it the full screen that you can see? Can I proceed on that basis? Okay, it's the full screen. Okay, thank you very much. So just to thank Billy and to thank Natasha and the Concrete Society. It's great to see the Concrete Society back in action again, and we hope that it goes from strength to strength. And also just to express my own appreciation for the opportunity to present this topic this afternoon, aggregates in concrete and appreciation of their role. You might just notice that I'm saying aggregates in concrete rather than aggregates for concrete, because aggregates are such an important aspect of concrete and its performance and behavior. So we really need to think about this as a composite material. I also this could be a dead, dull, boring presentation, so I'm going to do my best to make it interesting, but I also recognize that there are probably many people in the audience today who know a lot more about this, particularly in the practical aspects than I do. And of course, your experience could be shared at the end if that's appropriate. So let's get going. And just see if I can make this thing work. Here we go. So I want to talk, of course, there's an introduction, then something on classification of aggregates, main South African aggregate types. We then talk some detail on properties and effects on concrete. And there's a whole lot of stuff there to talk about, and then just something briefly on aggregate standards. Now, this is an interesting slide. I'd like you to have a look at it. Here are three polished cross-sections of three different materials. And the question is, and there's no prize, I'm afraid, for getting it right, which of these is a concrete? One of these is a concrete and others are not. So have a look, and yeah, we don't have opportunity to take any feedback here, but if you were to choose the top one, you would be wrong. But if you were to choose the bottom right, you would be correct. So that the top right is in fact a polymictic conglomerate from the Stain Reef and the Welkom goldfields. The one down at the bottom left is a quartz pebble conglomerate from the Ventersdorp contact reef. That comes from the Klerksdorp area. And in fact, the concrete is the one on the right. And the point I'm making here is that concrete is actually an artificial conglomerate. These two rocks that you see here are both conglomerates, the reef conglomerates, of course, the gold-bearing conglomerates, and concrete really is an artificial conglomerate, as you can see there. It's pebbles or fragments that are cemented into a matrix, and that's what we deal with. Okay, so in terms of aggregates, they are, of course, they are the granular materials that we put into our mixes. They can be of different origin. Usually they derive from rock, but not exclusively so. And the important thing here is that they make up a large proportion of the volume and the mass of concrete, somewhere between 65 to 75%, sometimes a little bit more, sometimes a little bit less, but that's a general rule. And as you can see in the figure to the right, that's where the concrete fits in. And for example, an ordinary paste, pure cement paste, fits in right up at the top. And you can immediately see that concrete, what the addition of aggregates does is that it hugely brings down, in this case, the relative shrinkage. In other words, it produces a material that is an engineering material. Cement paste is not an engineering material, except maybe as grouts and things, but it's not going to work for structural purposes. However, aggregates make cement paste into an engineering material by bringing down, for example, the shrinkage, hence producing dimensional stability and things of that nature, also improving many, many other properties. So that's important to understand. Here are some nice pictures. On the left, we have a typical hard rock quarry, which is a well-managed quarry. You can see the benching, you can see the drainage of water, you can see the roads and so on. A well-managed quarry there. And then on the right, you can see a typical stockpile, set of stockpiles with the cement silos in the background. And if you happen to notice, there's some mountains in the background. This was actually a picture that I got from George Evans on the Berg River Dam down here in the Franschhoek area, which was about 20 years ago. A good picture of stockpiles and how well they're managed. All right, let's get going here. Okay, now let's talk about classification. Okay, now there are different ways of classifying. The first way of classifying aggregates is based on their size. And so we have fine aggregates, which are generally classified as anything that passes the 4.75 sieve and is generally retained on the 75 micron sieve. And here you can see the standard, the South African standard for fine aggregates, SABS or SANS 1083. And the immediate thing to notice is that there's only 2 requirements, maybe 3. So you say to yourself, my word, you know, so can we do anything? And actually, in many cases, you can, because it's remarkable how you can make concrete out of a vast range of different aggregate sizes. And so in South Africa, we've tended to take the view that we're not going to over-restrict things, because we have to work with natural aggregates in sometimes very remote places. And if we were to be too prescriptive, we might knock a lot of aggregates out of the game, and that may have adverse consequences. Of course, there are preferred limits, and sometimes we call those the grading limits, like that. There's an ASTM C33. That's the ASTM standard, and you can see here are 2 concrete sand samples, A and B. Both of them would probably make very acceptable aggregates in concrete, but you can see that the one is in the grading envelope and the one is not. So just because it falls outside the grading envelope doesn't mean we can't use it. We need to look at each case in its own merit. We then get the coarse aggregates. These are, as you can imagine, particles that are larger than the 475, and I know we're changing to 5mm sieves and so on. I'm still working with some old sizes here. And interestingly enough, it's down to the 19mm that really fits that definition. If you start getting 13, 9, and 6 aggregates, you can see some material can fall below the 475 because these are the smaller sizes. But in general, that's the definition of a coarse aggregate. If we then look at the other way of doing this, which is based on the source. Here we have the first is the one that is by far the majority, the natural aggregates that we get from crushed rock. In South Africa, almost all of our coarse aggregate is crushed rock. Very little natural aggregate in the coarse range. And it's only the only thing that it's been subjected to is some sort of mechanical processing, but it could be natural gravels in some cases. Then the next lot would be manufactured aggregates. On the right here, we see an example of slag, a cooled slag, air-cooled slag with lots of vesicular vesicular voids in it from the escaping gas. That would be another kind. We then can get recycled aggregates, and here there's a lot more work being done on this at the moment, and some very interesting work. And the whole idea of circular construction that comes in here. We have to start using material, not throwing them away. So demolition waste, what can we do with it? We can make it into recycled aggregate. We have industrial byproducts, such as, in this case, glass or incinerator ash. And lastly, artificial aggregates. And these largely are used for lightweight concrete. Not much of this in South Africa, but if needed, it can be obtained. So this is the kind of classification based on source. Now, let's have a think about the main South African coarse aggregate types. And here, these are ordered. This list on the left is ordered more or less in the decreasing order of consumption. So quartzites and sandstones by far take the lead, and probably 70 or 75% of our aggregates. So these kinds of rocks come from these rocks. Then we get the basic igneous rocks, the dolerites, right down to the andesites. The interesting one here is the basalt from the Lesotho Highlands, which, if you've ever worked in the Lesotho Highlands, you'll know is quite a problematic rock, and one has to be extremely careful of that one. And then the granites, the grey wackies, which is our stock in trade in the Western Cape, at least in Cape Town, that is. The tillites, more or less from KZN, and then the dolomites, felsites, and others, the rest of them, all important in their own right, of course. So that's what we have. And here I've just tried to put down a table where if you can identify roughly where you are. Of course, these are the main metropolitan areas. If you're stuck out in the sticks somewhere, well, maybe this doesn't apply, but you can see in the different major regions, you can see the aggregates that are available, both fine and coarse. And it's interesting that certainly Gauteng, which is our richest province, also has the richest option of aggregates. So it really is, you can use different aggregates there, and sometimes to good effect. For example, the dolomites are very much in demand if you're doing sewer work, or even for concretes of low deformation capacity, high elastic modulus, low creep, etc. We'll see more of that later. Okay, now some of the properties of aggregates and their effects on concrete. First of all, grading. Grading is important. We can grade our aggregates. We use the sieve method. And in general, in South Africa, we tend to use what we call gap-graded aggregates. We do occasionally use continuous grading. And the little diagrams on the bottom right would show you some of that. In the gap-graded aggregates, there tends to be a size gap between the stone and the sand. So maybe 19 millimeters stone, and then the sand particles down at 475, and there's something missing in between. And that's largely because, again, of our aggregate sources and what we can do practically. It's possible to do continuous grading, but it's only used in particular cases. We then have fineness modulus. This is now an indicator of the average particle size. We need it for mixed design. But note that it's not an explicit measure. You can get fineness moduli for different sands of the same value, but they might have vastly different gradings. And so it's a general sort of guide, but it's not an exclusive one. Generally, we try and work between somewhere around 1.2, which is a very fine sand, up to about 3.5, which is rather coarse, but I've seen many cases where that goes up to 3.7, 3.8, or something like that. The fines content is important largely for giving us cohesiveness or cohesion, and it controls quite a lot on the water demand, also on the bleeding aspect. So that's that one. And here's an example of a fineness modulus calculation. You take the cumulative percentage passing the standard sieve sizes, and in fact, you can do this for stone as well, and cut off at the 150 micron. You add all of those numbers together, divide them by 100, and there you get the number. So this, it's a fairly crude measure, as you can see. Those gradings could vary a lot and still give you the same number at the bottom. But it's a number we use, and it's useful because it does give us a measure of the average particle size in fineness modulus units. Okay, now other properties of aggregates that are important. We get the bulk density, or densities in general. Bulk densities are the density of the aggregate in its bulk form. In other words, not in the pure rock form. We get the compacted bulk density. We use that for, again, largely for mixed design. And we get the loose bulk density, which is important for stockpile calculations and things like that. Then particle density, the density of the actual aggregate particle itself, sometimes known as specific gravity. And here, these are rock materials, so they're going to fall in that range, roughly 2.5 to 3. Siliceous aggregates, generally about 2.65. And then the ferromagnesians, those would be the dolerites and those kinds of things. They have some heavy minerals in them, goes up a bit. Also calcareous aggregates. And we need to take this into account. It will affect our mix proportions and how much of this material we can put into the aggregate, or into the mix, I should say. So that's an important, very important number, and we use it extensively in concrete technology. Right, moving on. Particle shape is an important aspect, surface texture and absorption. These three are really quite critical because they have very, very profound effects on water demand or water requirement for concrete. If you can see the figure up on the right there, moving from the top left and going clockwise, you sort of going from, let's say, the best particle shape, nicely rounded, right to the one on the bottom left, which is angular and flaky. And we don't particularly like that kind of shape in our aggregate because it usually causes a lot of internal friction and lockup. And then we have problems with workability. We like the sort of chunky aggregate shapes, which are at the top right or maybe the bottom right at the most. Those give us reasonably good concrete properties. The particle surface texture varies greatly from smooth to rough. I'll give you some pictures just now. And then lastly, absorption, of course. In South Africa, because we use largely hard crushed rock of fairly unweathered sources, usually our absorptions are less than 0.5%. In other parts of the world, that's often not the case. And if you start using a material like a recycled aggregate, you'll be up around 5 to 8%. So you really have a very different situation altogether. And certainly some of the Lesotho aggregates can have absorptions up to 3 or 4%. And that needs to be accounted for. It can have very significant effects on slump and particularly slump loss. So this really is an important parameter. Sorry, I seem to have gone out of my thing now. I pressed the wrong button. It's me. Are we right at the beginning again, Billy?
No, I'm still having a look at the same slide, showing that 6 pieces or 6 aggregates with the different shapes.
All right. Yeah, sorry about that. I usually get this wrong, but I'm trying now. Let's try now. Can you still see that? Okay.
Yes.
Down at the bottom right, there's the different kinds of moisture states, and the important one for us is the saturated surface dry state, which is the one about the third one to the right. Does the next slide come up, Billy? Is that okay?
No, it's still on the same slide.
Yeah, no. Mine has gone to slide 19. Yours hasn't.
No. But I can move it to slide 19. I don't know if I should be doing it, but I just moved it on.
Okay, so this is a bit awkward. Let's just see if we can make this work. I'm on slide 19. Are you on slide 19 as well, are you?
Yes.
Okay, let's go on slide 19. Okay, this is the definition of water requirement. It really is the amount of water required in 1 cubic meter of concrete to give the required workability. That used to be a 75 slump, but these days admixtures have hugely influenced this whole issue. So, you know, this question of water requirement has become a little bit moot because we can do marvelous things now with admixtures that we couldn't do when water requirement was first defined. And so they are really our process control parameter in many cases, although we always want a low water content, as we'll see. The fine aggregate always has a larger influence on this water requirement because of its larger particle surface area.
Sorry, Mark.
Yeah.
We still on slide. I'm on slide 19 because I moved to slide 19, but
yeah. I'll tell you when to move. Is that okay?
No, but if I move, the rest of the people don't see it. You're going to have to move it to slide 19 in some way.
I am on 19 now, Billy.
Okay. Maybe you should unshare and share again.
Shall I do that? Right. Sorry about this, everyone. Right. Am I still on mic here, Billy?
Yeah, you on slide 18. I can still see slide 18 still being shared.
Yeah. Okay, let's just get this right. All right, so you're still on slide 18. Let me stop sharing. I've just stopped sharing.
Mark, you don't have to. We can just advance it ourselves. I've just done it on mine.
Okay, no, thank you. Thank you for putting up with me. I'm still, there's a lot of people still being admitted here. So now I'm trying to share. Okay. Let's see now, share aggregates in concrete. Give it a moment.
All right, I've got your first page.
Okay, so I need to slide through these ones quickly.
Yes, there it's working again.
It's gone too far. To the left. Like this. Okay, now we're near the beginning again. Yeah. Okay, what do you see now?
I see aggregates almost cream colored.
Okay, so that's good. That's where I want to be. Background. Okay, thank you. So let's just run through a few slides showing these features that I've been describing. Here is a sand. It's a natural sand. And you can see it varies from quite rounded or subangular particles to now I've lost control. Somebody took control and now I've lost it again. Okay. Sorry. I'm trying again. Now we're in the beginning again, right?
Yes, in the beginning.
All right, I think we're there again. Do you get that same picture again?
Yes, that same picture, slide 20.
Again, I apologize for this. Okay, this is a sand, and you can see it varies from really good particle shape to very angular and flaky. and variable surface roughness, as you can see. If we look at the next one, this is a crushed Witwatersrand quartzite, really beautiful particle shape, generally clean, smooth surfaces, a little bit of rough here and there, but really a nice sand. The next one would be this one. Okay, here again, this is almost what Consol uses to make glass with. It's almost pure quartz, very nice particle shape, very clean surfaces, smooth, and so on. Here is now another sample of crushed Wits quartzite. Very, very poor particle shape, highly angular, flaky, all the kinds of stuff you don't want to see, and somewhat rough surface texture as well. If we look at this one, well, you can see what you can see there. You might think those were some cookies, actually, but they're not for eating. They are some kind of natural aggregate. And if we look at this one again, a very smooth, well-shaped aggregate. A nice stone there, but with quite a lot of rough surface texture, but very nice particle shape. So you can see how this thing can vary. And lastly, this is again that picture of slag. Now, over that whole range of aggregates, the difference in water requirement, if those were used in concrete, would probably be about 50 liters per cubic meter. Now, you take a water cement ratio of 0.5, that would translate into about 100 kilograms of cement. If you use the most, let's say that was the lowest water demand.
A text message to say that we're moving him to that time.
I think sorry? I think we have somebody on mic there. If we were to use the one with the lowest water demand versus the highest water demand, that would cost us about 100 kilograms of cement. You can do the maths. You can see what effect that would have on cost. So as Steve Croswell used to say, there is the saying, the combination of cheapest ingredients is not necessarily the cheapest combination of ingredients. You can think about that while we go on. Okay, now let's talk a little bit about the interfacial transition zone. This is the zone between the cement paste illustrated to the right there, which is composed of calcium silicate hydrate, some portlandite or CH, and then the ettringite, and the aggregate, which is to the left. It's this narrow zone which really governs the cement paste aggregate bond. And if we look at it, this kind of schematic here, you can see that up against the aggregate, which is on the left, you've got very high porosity. That's the solid line, and that quickly comes down and then sort of settles down into the bulk paste. And on the other hand, the calcium silicate hydrate, which is the gel or the paste itself, the hardened paste, then comes from a lowish value up to a plateau at the higher part of that diagram. So this zone can be very porous. It can be of low strength. It can be low stiffness. And the consequence is that it strongly influences, first of all, the cement paste aggregate bond. And secondly, it maybe even more importantly influences the stiffness of the whole system. Stiffer ITZs allow greater mobilization of the aggregate properties, and we'll see that just now. So the ITZ, we've realized in the last, say, 2 decades, is really a very, very critical part of concrete. And we've also learned how to control this zone. So we can control it if we know what we're doing. Let's think now of some concrete strength and how it's affected by aggregate properties. I've highlighted there in red what I think are the most important factors. There are a bunch of them there. There's aggregate type, the aggregate paste bond, the nature and influence of the ITZ that I've described, the surface texture, the elastic modulus. These are important, probably the most important ones, and aggregate size too. There are some others as well, but I won't deal with them now. Here's an example of some work. Now, I've been working in aggregates since the 1980s, so that goes back a while. This is work we did way back then, where I'm not even sure it's still relevant, but certainly in the aggregates we were working with then, from all over the country, you can see that in this case, we were still working with cement water ratio. So take a cement water ratio of 2, or that becomes 0.5 water cement ratio. And if you look above the 2 here, you can see that the difference in concrete strength could be well below 50 megapascal up to around 60. So maybe 10 to 15 or 10 to 12 megapascal at exactly the same water cement ratio for different aggregates. And this is something which the aggregate people understand, and they make a good use of it when they do their marketing. Of course, you have to have these aggregates available. It doesn't mean that they're all available in every area. When it comes to aggregate strength, obviously, we are using or working with the material in its granular form. We can take rock samples or rock cores and test the unconfined compressive strength, but usually we test this in an indirect way through either the aggregate crushing value or the 10% fines aggregate crushing test. Essentially, you take a sample of graded aggregate, a certain grading and a certain mass, you put it into the steel cylinder, and then you really just crush it under a loading machine, and either measure the percentage fines that you create or the load to give you a 10% fines value. Let me just get a bit of water here. So that's the 10% fact test, and usually we're looking for fact values around about 110 and higher for a good competent aggregate. Dimensional stability of aggregates is important because this affects shrinkage, creep, and we'll see that a little bit of time as well just now. So let's talk about concrete deformation properties. In many ways, the aggregates affect these properties even more than strength. And these are stress-strain relationships, elastic modulus, shrinkage and creep, and thermal strains. And again, this was work from some time ago. Just taking a swig of water there. Here you can see an even more graphic outcome of some of the testing we did. Here are a whole bunch of aggregates here. They vary from dolomite through dolerite, andesite, grey wacky, all the way down to siltstone. And if you look at a typical concrete strength, let's take 40 megapascal, you can see the aggregate, the modulus of the concrete could be somewhere around 25 to 28, all the way up to 45, almost double the elastic modulus of a concrete of given strength. Now, once again, not all these aggregates will be available in every geographical area. But if you want a concrete of high elastic modulus, you need to really go for what we would here call a Transvaal dolomite. Not every dolomite does this, by the way, but these are the Transvaal dolomites. Really, really superb materials in giving you high elastic modulus. We used this to good effect when we were doing repairs on the M1 motorway in Johannesburg many years ago, when we needed to do an infill concrete of very low deformability. So that is a very interesting graph. And here's an even more interesting one where taking the dolomite concrete and looking at the difference between the 28-day values of strength versus elastic modulus, which is given here in the dashed line, versus the solid line, the same concrete, if we allow it to mature for 6 months, you can see the vast difference. So, for example, more at the lower strengths, you can see that we can again push that modulus up from under 40 to close to 50 by maybe 10 gigapascal. And this has a lot of importance when you're doing things like calculating long-term deflections. The difference between the short-term elastic modulus and the long-term elastic modulus could make a huge difference. And this needs to be appreciated. Again, not all aggregates will do this, but every aggregate has its own fingerprint, if you like, and needs to be understood. This effect that we see on this diagram is really largely an effect of the interfacial transition zone. It represents a densification of that zone with time due to ongoing deposition and hydration within that zone. We can actually take that effect out. We can sort of engineer this zone by using very, very fine fillers, SCMs like silica fume. Now, talking about shrinkage and creep, two important properties of concrete. Aggregates affect, as we saw right from the very beginning, they affect this very profoundly. And there are two effects. It was what we call the dilution effect, which is simply the figure that we saw earlier. I'll show it again now. And the restraint effect, which is due to the stiffness of the aggregate. If it's a stiffer aggregate, it tends to restrain the paste movement and tends to give higher elastic moduli, lower creep, lower shrinkage. And we've seen the one already here. This is the dilution effect. Coming down again, remember the concrete, these last 2 points on the bottom right. And you can see there that the concrete is producing shrinkages, in this case, are less than 20% of the paste. And so that's the dilution effect, very important. And then if we look at the restraint effect, here is one over here. So for example, there are the dolomites. This is relative shrinkage for a range of South African aggregate types. We've got all of them here in that legend. And up at the top, there's the dolomites. They are very low shrinking materials, in concrete that is. And down at the bottom, we've got a siltstone, which is a high shrinking material. And you can see exactly what it does to concrete shrinkage. And here again, the shrinkage could differ by a factor of 2, depending on the aggregate type. This is really critical when you're looking at deflection-sensitive structures. Here's the creep curve. Again, the dolomites, really very low creep up top here, which may or may not be a good thing. I'm not saying you always need low creep. You sometimes might need higher creep. Down the bottom here, not so much the siltstone, but the quartzites. And the other important thing to notice here is that the quartzites vary all over. So they pop up all the way down this graph here. So you can't generalize on geological type. Maybe with the Transvaal dolomites, but other dolomites may not do the same thing. So again, every aggregate having its own fingerprint and having its own particular properties. And this is the one, again, the restraint effect. If you plot total strain, which would be elastic plus shrinkage plus creep, under sustained compressive stress here of 5 megapascal versus the elastic modulus. Okay, there's a lot of scatter on this graph, but the general feeling or the general trend is there. Higher concrete elastic modulus, lower total strains. Likewise, in the thermal effects, I'm not going to go through this in detail, but you can see the cherts give you quite high coefficients of thermal expansion in concrete, marble very low, and limestone somewhere in the middle. But most of our aggregates give concrete thermal expansions or coefficients of around about 10, which is what we want, really, in many cases. What about concrete durability? Very briefly, I'll bring this thing to a close now. Of course, again, aggregates here, paste is not a durable material in effect. But when you put aggregates in concrete, you can produce a durable material because the aggregates are generally the most durable component of a concrete. They are not susceptible to leaching or to acid attack and so on and so forth. And here on the right, you can see sometimes we get internal lack of durability due to aggregates. Sometimes they can cause problems. Mostly they don't. But here is an alkali-silica reaction diagram at the top right. Very common in the Western Cape, where you can get really quite severe deterioration with time. And on the bottom one there is what happens when you get different kinds of aggregates in concrete attacked by acids. And in this case, on the right is an aggregate that is acid susceptible, and on the left one that is not acid susceptible. And you can see the difference between the overall effect on the concrete. And here is a diagram. This is actually from Fulton, where I'm just going to mention that the most common ones that we deal with in aggregates here are the alkali aggregate reaction, which will be the subject of the next talk next month, and acid attack, which particularly is occurring in concrete sewers. There are also physical mechanisms, surface abrasion, freeze thaw, surface wetting and drying, and so on. Won't go into that in any detail. Lastly, there is the question of aggregate standards, and I've just stuck some down here for you. These are important because they do tell us what we can do, although, as I've said, that in many cases, we may have to be willing to work outside of these standards, provided we have evidence that the aggregates we're working with will meet the performance requirements. So these standards at this stage are still prescriptive. They tell you what you need to have rather than what they need to do. And there we need to slowly move towards more performance type standards. Our aggregate standard is still SANS 1083, which is still waiting finalization for the latest version. But there's the Indian standard, the ASTM, and the British standard as well, which is an EN standard. So they lay out the primary requirements. They specify the standard tests. But the point that I want to make is that sometimes we have to work outside of those limits just to get a concrete that might work in a very difficult situation. Okay, so these are some of the references I've worked with, and I want to acknowledge these kind of people. Steve Croswell, who was a great colleague here in the Western Cape, retired now. The Fundamentals of Concrete book and Fulton's Concrete Technology, of course. So I'm grateful for these references. And lastly, thank you for listening, and if there are questions, we can try and take them now. Thank you so much.
Thank you very much, Mark. I think we can all give him a thumbs up, react, or if you really want to do a thumbs down, but just give our appreciation, and hope, Mark, you can see that all on the screen.
Yes, thank you. It looks quite something.
Yeah. Now we're going to open the floor for questions. We've got another few minutes. So you can either raise your hand or you can type it in the chat box. I will be managing the chat as well, or I should. I mean, there it is, yes. So you can raise your hand or ask a question, and then hopefully we'll get the right answer.
So Billy, you're going to lead off with the questions, are you?
I'm going to have to ask a question.
Yes, please do, and then I'll answer if I can.
Aggregates, just a question of all your research. You've done a lot of research in 1980s and 90s, but
Yes.
concrete technology has changed a lot. Admixtures has changed. Cement
Yes.
has changed. How relevant is those research results still today?
Well, it's a good question. I mean, aggregates have also changed. You know, the reef quartzites we had then and so on would it be different? I think the point here is that aggregates are still have this profound influence on concrete properties. And we've got some different kinds of cements. We've got admixtures that can bring down water content, which is good. We can engineer the ITZ. We can do a lot more things, but the fundamentals remain. And the point that I've been trying to stress is that every aggregate actually has its own influence on concrete properties, and people who understand aggregates will be able to make the best use of anything that we've got, the newer materials, to produce good concretes. But I think the principles are still pretty much there, even though the research, as you quite rightly point out, is a bit dated now, but some of the work that we're doing now is still bearing that out. Thank you.
There's a question here from Dr. Megan Brink. With the E-value results, what specimen shape and size was used?
I think you're talking about the concrete E-value. I think we used prisms, as far as I remember, 100 by 100 by 200 prisms, and we did it that way. I might just mention that here again, the ITZ can have a huge influence. So if you cast your concrete in one direction and test it in another, at an orthogonal axis, for example, you could get a quite different result. So there are all these things to bear in mind, but that's how I think how we did it.
Maybe while we're waiting for another question, I'll just do a quick advert, is that he didn't really speak about ASR at all in this presentation. And that's a very crucial aspect of aggregates. And that is because there's a whole lecture, a whole presentation next up. I can't remember the date out of my head, but you would have seen it in the emails, about ASR by Janina Kanji from WIT. So stay tuned for the next presentation for ASR, alkali silica reaction.
Yeah.
Are there no further questions?
Yeah, I've seen the question there. Comment on the availability of local aggregates. Well, as far as I'm aware, the rocks haven't moved. So I think they're still available in the main. As far as I'm aware, I don't think there are any particularly new sources. However, we are finding some very interesting things. For example, take the Table Mountain sandstones. In general, they are very good materials, but if they're a little bit weathered, they can give you some really very low stiffness values and strength too. They can also vary hugely with their alkali silica reactivity, from almost innocuous or pretty well innocuous to really highly reactive. And that's just reflects the variability of the geological sources of these materials. So in general, these materials are still available. We're doing quite a lot of work in the Western Cape on recycled aggregates, trying to work towards a circular economy. And at this stage, it looks like those are best used in concrete products rather than concrete, sort of normal structural concrete. I hope that helps. And here's another one. Okay, on another note, what shrinkage standard? Yeah, I'm not sure what standard I prefer. I'm not sure if you mean there the standard on what shrinkage is allowable or the test. There are the accelerated shrinkage tests, which will give you some sense and of course they're used in specifications. But when we do long-term shrinkage testing, when we do with creep testing, that is the one that gives you a more, let's say, realistic view of concrete. But the accelerated tests do give you a sense of what you're dealing with. So I don't know if I can particularly comment more on that. The size of the coarse aggregate, the hardened properties. Yeah, will there be a noticeable difference between 13 and 19 aggregate? Well, of course, the point here is that the larger the size of the nominal size of aggregate, the more you can put into a mix. So a 26 millimeter aggregate, you can put more stone into a 26 millimeter aggregate mix than into a 13 or a 19. And of course, if you can get more aggregate into the mix, you're going to certainly benefit the technical properties and increase something like stiffness if you're concerned about that. So it is this matter, that's where as I've said before, this is a generalization that I've been dealing with, and each case has to be considered on its merits. But in general, a 13 millimeter versus a 19 would have more paste or matrix in it, and you might expect a slightly lower modulus in a case like that, for example. Another question here, is it advisable to use reclaimed aggregates from old concrete structures? Well, I'm not sure where else you get it from, but certainly the demolition waste is not a waste anymore. It's a resource. We need to think of it as a resource. It's very interesting in Cape Town. About 10 years ago, only about less than 20% of demolition waste was being recycled into recycled aggregates or hardcore or base material or whatever. There was a bylaw introduced a couple of years ago where every building that was being demolished had to have a demolition certificate saying where you're going to put this material. Those recycling rates have gone up to 70%. So a simple piece of regulation has hugely changed the situation, and now every last piece of demolition waste, if you like, is being viewed as a resource, and that's a good thing. So the problem here is that the variability of source, that's the big issue, variability, as we know. So if you can get a really nice stock of recycled an old building with more or less consistent concrete in it, you're onto a good thing. Hope that helps.
Thank you. Is there any other questions? Are there any other questions, I should say? Doesn't seem like it. I think I want to thank Prof. Mark Alexander one final time. Thank you for the time. Thank you for the effort presenting this work. We really appreciate it, and it falls very nicely in our concrete class series. Thank you very much for taking the time. Thank you also to the audience for coming to listen, supporting the Concrete Society. As I said earlier, consider becoming a member. And yes, then I see everybody at the next Concrete Fix, which is the, Natasha, 22nd.
24th.
24th of
Yes.
April. All right, so I want to end off here.
Sorry, Billy.
Yeah.
Jonathan Saunders has got his hand up.
Okay. Jonathan. Okay, I can't hear you, Jonathan. Can't see where you are at the moment. Okay, I think I'm going to call it here. Thank you very much. Sorry, Jonathan, for that. Thank you very much, everybody. Have a lovely evening and enjoy the rest of the school holidays. All right, bye-bye.
Bye.
Thank
Bye-bye.
you. Bye.
Bye.
Thanks, Prof. Bye.